All right, folks, we're going to be talking about solving some trig equations today. So this is going to bring some of the knowledge that we learned in section 1 when we go to get our answers here. Now, in class, what I had folks do was break off into groups to split up the problems 1 through 3. So because we did that, I'm going to just have you try problem number 1 here, both A and B. And then we'll go over the other two together and kind of see the differences when we're looking at sine as the parent function versus cosine and tangent. So read through this information, and I want you to attempt A and B, and then we'll go over it together. So hopefully you remember from our first section, when we're dealing with inverses, like our first step was to draw it, but inverses, when we're talking about expressions, only have one answer. When we're algebraically solving here, we're trying to get theta by itself. To get rid of sine, we're using the inverse sign on both sides. This is the part of geometry that you really just skipped over, writing that left-hand side to see those cancel. But that's the math that's happening behind this. So this isn't one where we had to use the inverse algebraically because it's something we can get without our calculator just by drawing a picture. So sine can be the square root of 2 over 2 in 2 places. It can be in first quadrant, and that's what your calculator will give you. And then it also could be in second quadrant because when we think about a positive square root of 2 over 2, it could appear in 2 places. But the reason we focus so much on this inverse is because there's going to be problems like B where we can't algebraically see these answers because they're not nice special triangles that we're used to. So we have to use that inverse and understand which answer our calculator is giving to us. Because an expression, remember, only has one answer, whereas an equation, when it's periodic, has infinitely many. So these are 2 of them, and we're solving for theta. So I can say my theta here, based on this special triangle, is 45 degrees. And I do want you to write these in radians. It says write them from 0 to 2 pi, so positive radians specifically. We got pi over 4. And then this one, as a reminder, once we know that fraction's over 4, using about 4/4, 1 backwards from that is 3/4. But another thing I had you think about is how we could write all of the solutions, because there's infinitely many, using just these 2, and kind of remembering what we did with tangent's domain. So when we talked tangent, we had asymptotes show up a same distance away. So we found one of them, and we said they happened every period after that. We're going to use a similar formatting for these. When we think about what's going on here, this is the graph of sine. And we're looking at where it's square root of 2 over 2, which is like 0.7. So really, we're thinking about all of these points. And there's infinitely many. But we found the first 2. We found this pi over 4, and we found this 3 pi over 4. But then the infinitely many comes from on the unit circle, continuing to lap around and around. So what we want to do to generalize is see if there's a pattern between any of these infinitely many solutions. And in the case of the first 2, that distance between them is pi over 2. But then if I go to the next one, visually you can see that's bigger. On the unit circle, that angle's a lot larger. So if they're not all equally distanced, we're not going to be able to group them all together, but we can group them just by their laps. Okay, so how that works is we're going to treat this kind of like if it were a piecewise function. So we'll start with theta equals, because we're solving for an angle. Then we'll open a set bracket where we have stuff stacked on top of each other here. So we're going to say the first angle, pi over 4. But then I can say, well, I can get another solution by going another lap around the circle, or another period if I'm thinking on my graph. For sine, that's 2 pi. And how this is similar to tangent with our domain is we're saying we could add 2 pi 1 time, or 2 times, or 3 times. We say that any number of times, so times n, as long as n is an integer. And then that same thing happens for the second one. From here, I can add a lap forever. So we'll use 3 pi over 4 plus that period n again, as long as n is an integer. Okay, and so if you struggled at all with the second one, it was because that's not a nice triangle. You still drew them in the same places, but sine of 1/3 is not something that you just know. And that's where the algebra comes into play when we're doing it today. The algebra is to get rid of sine by using the inverse operation. So that's inverse sine. And we're going to just toss that in our calculator. We know an angle is going to be from 0 to 90 based on the quadrants you drew it in. And we're just going to use our calculator to help. Okay, so it's about 19.5 degrees. But again, the picture is helping us because we only have one answer from our calculator, and we have to use the symmetry in the picture and what we know about the unit circle to find the second one. So here, kind of like what we did in radians, if this was 4/4 pi, I just had to go backwards, whatever that angle was, or 1/4 pi, that this one was. In this case, our angle is this 19.5, and sometimes it helps to actually type it in there. And I know closest to that is 180, but it's not quite there. So I can take 180 minus that number to get the second one. And that's about 160.5. Okay, but just like we did this one, it asked for this in radians. So I wanted to show you this pattern here, but what we're going to do is actually find the first one in radians, and then go back to the idea of using pi versus 180 for the second one. Okay, so go grab your answer again for the 19.5. We want to make sure we have the whole thing. And what we're going to do is convert that to radians. So to convert that to radians, we're taking it times pi and dividing by 180. Because these aren't nice numbers to start with, we won't just divide by 180 and change it to a fraction because it won't be rational. And if that part's going to be rounded anyway, we're going to type this whole thing in at the same time. So here, it'll be times your pi, divided by 180, all in one go. And that's about 0.3398. We're going to use 3 decimal places. That's what it asks for later in the instruction. So that would look like about 340. And then our second one, we're going to just use this same formula that we talked about with degrees, but if it's radians, that will change to pi. So my second answer is just pi minus theta from symmetry. And that's our supplements theorem that we talked about in Unit 3. So grab pi and take it minus that number. Okay, and then we're going to talk about what these actually mean. So this is 2.802. Remember, pi is just a number, the irrational one that's like 3.14. So hopefully it's reasonable to you that this first one is pretty small. Okay, and then the second one is closer to 3 because it's closer to that pi value. Okay, so think about those as you're coming up with the answers from your calculator to know that you're doing the right math. We're going to generalize the same way. This one I'm putting approximately because we did round. But the first one and the second one is not the same as when we keep going around the circle. So we can't group them all. We're going to stack them on top of each other just like the last one. Because we're dealing with sine again, it's still 2 pi n, where n is an integer. Second one came. Okay. So the next ones are very similar. Okay, cosine, when we're thinking square root of 2 over 2, that's first quadrant or fourth quadrant. And because it's cosine, we focus on this side of the triangle. Either way, it's still a 45 triangle. So something in common with the last problem is I still have pi over 4 as an answer. What's different is I need now this angle here in quadrant 4. It's not in quadrant 2. So to get there, we can go all the way around. Okay. This 2 pi in fourths is the same thing as 8 fourths. We're not quite there, going backwards 1. So that'd be 7 pi over 4. Because again, these aren't the same distance, we're going to have 2 stacked on top of each other. Pi over 4, add a left, so plus 2 pi in. And then from this one, the 7 pi over 4, add a left. Now I want to chat for a minute about inverses. When we talk about the inverse cosine, we know that it's going to give us an answer here or here, so this wouldn't be an option. But with inverses in general, they usually talk about quadrant 4 as clockwise. It actually is okay in general to write this as a negative pi over 4 or clockwise pi over 4. In the case of this, the reason I didn't is from these instructions right here. Those instructions are not going to be included for your homework. It's just going to say, write the generalized pattern, write the generalized solution, which means you can get any version of those 2 points you want, clockwise or counterclockwise, whichever is easiest for you to see. Okay, so let's check this next one. Still same position. We've got this 1/3 along the side. Same concept as last time. This is not a nice triangle. So to solve for theta, we just do the inverse cosine, and we're going to do some calculator work together here. We know it's not going to be a nice triangle, so this is going to be a pretty ugly decimal when it comes out. So inverse cosine of that 1/3. And it helps a little bit to do the math in degrees, just so we can think about the numbers. So this first one will change to radians, no problem. But if I want to think about this point, it's closest to this 360, but it's not quite there. So this second one is going to be 360 minus that angle that we have. In radians, that would mean 2 pi minus the angle. Just using our picture to kind of help us get reasonable values. Okay, so let's go ahead and change that to radians. Times by pi, divide by 180. And we're using 3 decimal places again, like last time. So 1.231. And then the second one, we decided 2 pi minus that number. So 5.052. Okay. No general pattern between all of them, so we just stack them and add the 2. Last one here of these practice problems with our different parent functions looked at tangent. Tangent is 1. It's not at the original points for this one. Tangent is 1 when sine and cosine are equivalent. The only time that happens is with our isosceles triangle, the 45, 45, 90. Okay, but tangent is positive in more than one quadrant, just like the other ones. It's also positive down here because we have a negative divided by a negative. So we still got 2 locations even with tangent. And we're going to generalize their solutions. So the first one is pi over 4 based on our 45. And then over here, I know this is 4/4. 1 past it is 5/4. Okay, but we're looking in this picture, another way to kind of help with this is from here to here is a half term, or adding pi. So I could take this original pi over 4 and add 4/4 to get to 5/4 as well. And that conveniently happens again on the other side, which means tangent is going to be a special case for us, where we don't have to stack 2 on top of each other because we can group all of the solutions together. just like with tangents having equally distanced asymptotes, in fact, any value is going to be equally distanced. If I think about 1, that's here, and then the next one is that same distance away, and then that next one is the same distance away. So we're always dealing with that distance of, in fact, pi, which is happening because the period of tangent is pi. So I only have to write 1 for tangent, always. Okay, with that in mind, that's going to make our life a little bit easier over here, because if your instructions on your homework are just going to ask you for the generalized solutions, you really just have to find this 1 using your calculator, and then you can say add pi from there. Okay, so let's talk about how to get that 1. Again, this is not a nice triangle, because this is either you can think opposite over adjacent, or you can think y over x. But either way, when we think about tangent, our nice values are going to be 0, undefined, 1 over the square root of 3, which we call square root of 3 over 3, or the square root of 3 itself, okay? That's not happening on these ones. Don't be fooled by the 3 there. This is not a special triangle. We're just going to use the inverse of it. And we practice so much in the beginning because really, if you want to use your calculator for all of these, no problem. You just have to be careful that you recognize exact values like 30, 45, 60, and write them in exact radians, not the decimal version. So we've got about 18. Again, I like to look at the decimal version of the degree, just to kind of help you with the math if you're trying to generalize. We already talked about in this case, we just need to change it to radians because we don't necessarily need that second one. If you wanted it, you'd add 180, or in our case of radians, pi. Okay, we're going to take this times our pi over 180 to convert. And we just need that 1.322. Adding pi in to get all of them after that. Okay. So now we're just going to practice some other problems, recognizing some differences that could show up. This first one, it says we want to know all the solutions where sine of an angle is equal to cosine of that angle. So we have problems where we're going to be able to draw triangles or exact values and just solve by looking at this. And then we'll have other problems where we're going to need our calculator to help us a little bit. So the only way you're going to be able to use your calculator, though, is if you have numbers involved. That tells us this problem right here we can draw out. So we're going to start by thinking, where is it possible for sine and cosine to be equal? So just focus on sine, like positive and negative for a second. What quadrant has both of them positive, and what quadrant would have both of them negative? Okay, hopefully you're okay with that being 1 and 3. And then we want to think about actual values. This is saying what kind of triangle has y and x the same, or this side equivalent to this side, and that's a 45-degree triangle. So we just want the general solution. I don't necessarily need both of them. I just need to generalize the pattern. A lot of times you'll need to list both because there's not an equal distance. This is one of the special cases where we can put them together because we're seeing kind of similar to what we had last time, where they're halfway across the circle or pi apart. So our first answer is pi over 4 from this one. And I can say they happen every pi after that. And that's it. Okay, the next one, you'll notice there's some extra numbers in different places we're going to have to solve. Okay, think about order of operations. We're trying to get theta by itself, and we're going to solve old school style, moving some stuff around. So I've got now tangent squared theta equals 1/3. And we know to get rid of a squared, we take the square root. But I want to talk about something for a minute. So let's think about x squared equals 4. We know that that answer is 2, but the answer also is negative 2. And it's because we're saying there are two x values that I can plug in here to equal 4. Okay, this is another significant difference between an equation like x squared equals 4 and an expression where I just ask about the square root of 4. If I just ask you square root of 4, the answer is 2. But when I talk about an equation, there's a plus or minus possibility. So for us, when we see this equation, we're going to have two answers, plus or minus. And then remember, square root at the top over square root at the bottom for fractions, which gives me the tangent being 1 over the square root of 3. So I'm going to rewrite this. Tangent is plus or minus 1 over the square root of 3. And that's what we're going to visualize. So because it's plus or minus, we have to talk about all of those possibilities. A positive 1 over the square root of 3 for tangent could be in quadrant 1. Or we could have it in quadrant 3. Then the negative is in the other two quadrants. So really, when we see this plus or minus, we're going to have all 4 quadrants. Which actually makes our life a little nice, because that means there's going to be something that we can generalize automatically. Okay, well, let's talk numbers. So remember, this can be written as opposite over adjacent or y over x. And you'll notice I chose not to rationalize that. That was intentional. It's not our final answer. The angle is. So this version is actually going to help you. Because if I can see this 1, and I can see the square root of 3, and that's going to trigger in my memory the 1/2 and the square root of 3 over 2. Remember, tangent, when we have 1/2 over the square root of 3 over 2, the 2's ended up canceling out. So start with those values, the unrationalized version, and that's going to help us decide that this is actually a 30-degree triangle. So first angle here is pi over 6. Okay, and we don't necessarily have equal values through all of them. Let's check it. I know this distance is 60, 30 and 30. Then here, to get a right angle, that would be 60 and 60. So that's 60 total here, but this is 120 total, so they're not equally distant. And unless you draw your triangle super accurately, you're not going to know that obviously, so do a little bit of math. And then, that tells us we can't put all 4 together. But, just like what we did over here, if they're across from each other diagonally, we can group them together. So I'm going to group these two by saying plus pi n, where n is an integer. And then I'm going to do the same thing for these two and group them. So let's talk about this angle. Same thing we've been doing. This is pi, and my fraction is over 6. I can call it 6 pi. I'm not quite there, so I've got 5 6 pi. Make sure you get your big equals. And there are your solutions. Okay. What I'm going to have you do now is pause the video and try questions 6 and 7 for me, and then we'll check it. Okay, so this first one, when we take the inverse sign of a negative, this is going to give us a clockwise angle. Okay, we talked about this when we were dealing with inverses. When you have a negative ratio, we're in quadrant 4, and they're going to give you the answer from our restricted interval, negative pi over 2 to pi over 2. So it's going to be a clockwise angle. So when you see that negative, it just means clockwise. So it still helps us to think about this 11.5 degrees, so we can talk about the math to find the other angle. Okay, so from here, I know that this is 180. I'd take 180 plus that number. But if we're in radians, we're really taking pi plus this number. The number in radians that we're talking about is this 0.201, but it can't be the negative version. Because if I'm adding the negative, I'm really going backwards this way. So it's really important when you're dealing with negatives that you're checking that your number is reasonable, thinking about your answer. Okay, so here, if I want to take pi plus this positive version, I really just have to take pi minus, and I'll explain this here in a minute, pi minus that whole number. When we see this minus a negative, that goes to plus. and it visualized that positive pi and a positive 0.2 that we're putting together, which now is a reasonable number because this is about 3.14, and we have to be past that if we're going this counterclockwise direction. Okay, so this one's about 3.342. But I want to emphasize something. If we go back to this problem with sine at the beginning, that's exactly what we did for this one. Okay, we took pi minus the angle to get the second one. So what we really just learned is it doesn't matter where the triangle is located. I can always find the second angle by taking pi minus that value if my parent function is sine. Okay, but the picture just kind of helps you visualize that, so it's not a memorization thing. Okay, then they're not equal distance all the way around. I just add my 2 pi n to both of them. Okay, the next one was another plus or minus, so we had 4 triangles, but they were nice triangles. Square root of 1/4 is 1/2, so they ended up nice, and it actually looked a lot like our Tanya picture. You're going to see the same types of answers over and over again, just like we have in previous chapters, because we've only got so many of those nice angle measures. We're going to briefly go through number 8. It's very similar to what we've been doing, but I want to talk about that, a conversation we had with number 2 again on this one. So based on the looks of this ugly decimal, this is probably going to be one that we're just using our calculator for. Okay, but if we think about cosine being negative, we have here or we have here. And so when our calculator gives us the answer, it's going to be this version, because we know our restriction is from 0 to pi. Let's see that happen. Inverse cosine of that negative 0.52. And then we'll go ahead and change that to radians right away. And we're seeing about 2.118. And hopefully that makes sense again, because this is 3.14. So it has to be a little less. Okay. Now one option that we can do is a bunch of math to get this angle. But what I want to point out here is some symmetry. From our first problem, we had this as pi over 4, and we called this angle down here 7 pi over 4. But I told you, because your instructions won't necessarily say use the positive version, you don't have to. If it's easier to go clockwise, negative pi over 4. That's something that for cosine may be faster. Okay? If we're dealing with cosine, you're going to have symmetry up and down, which means clockwise and counterclockwise are the same. That's our opposite theorem. And with that, we can save some time writing our second answer, because we can just go plus or minus the same direction. So we've got 2.4118 plus 2 pi n. And then going the other direction, same size, not same direction, we can just go negative. And that gets all my answers. If I wanted to find this version, okay, same math could apply as what we talked about on number 2. You can take 2 pi minus the angle, and that would give you that same version, positive, a little bit more than that 3.4. I know the last few here look a little scary, but I want to take you back to some algebra. And instead of focusing on this version, we're going to do some substitution here to make our life easier. So I want you to imagine this doesn't say cosine squared. We're just going to substitute a variable here and call it x squared. Now I want to emphasize, I'm saying x not because it's cosine, but because I'm just calling it some random variable. Okay, then this would be minus 5x, and then minus 6 equals 0. And that's a quadratic equation. When we talk about quadratic equations, there's lots of ways to solve them. One of them is factoring, and that's what we're going to focus on today. Okay, to factor something like this, When this just says x squared, there's only one way to multiply to get there if I want two terms. And that's x times x. Okay, this is what we call easy factoring in Algebra 2. And then I was looking at the factors of negative 6 that added to be negative 5. And that's a negative 6 and a positive 1. And then I would just plop those in. If I FOIL this back, you don't need to write this, but I'm just going to show you. X squared plus 1x minus 6x minus 6. This is equivalent to that original. You're just writing a factor of 1. But we do that because that allows us to say that this times this is 0, meaning either this first piece is equal to 0 or this second piece is equal to 0. So I know that x could be 6, or x could be equal to negative 1, or they could both happen. How this helps us is now, once we solve this part, we can do some substitution. And in fact, I usually don't even wait till that point. I just write it at this point. We're saying cosine minus 6 and cosine plus 1 equals 0. So this says cosine equals 6 and cosine equals negative 1. And the reason I use at that point to substitute back is it's telling my answer is not 6 and negative 1. That's the cosine of my answer. Okay, so I need to still find the angle. Okay, so now we can draw visuals for this, and again, it looks like two processes, but a lot of times with these, they're not both actually possible. Think about the graph of cosine. Cosine has a maximum of 1 and a minimum of negative 1. There's no way for cosine to be 6. If you try to type something in your calculator, if you're like, oh, that's not a triangle, I know, I'll just put it in, it's going to give you this domain error because that is outside of that output. It's just not going to happen. So that just goes away. And a lot of times that'll happen where one just disappears. Okay, remember, extraneous solutions are possible. Then, on the other one, we got cosine equals negative 1, and that is a thing that's possible. And when we see cosine being 1, negative 1, or 0, those are our nice original 4 points. So thinking about x, that's going to the left one. That helps you go ahead and write your ordered pair so you can see it. But remember, the goal is the angle. So the only angle that gets us there is pi itself. And then every lap after that, we'd have another solution. So we've only got one, just pi. Then we add every period after that. That's it. We're going to do this one together as well. This one, again, let's do some substitution. Call that 2x squared plus 1x minus 1 equals 0. And from here, we're going to try to factor or come up with our factors so that we can do some substitution. Now, some of these, and this is not the way you were necessarily taught to factor, but some of these, you don't have to work too hard if you kind of think about what factoring does. It splits this 2x squared into something times something else. Now, in the case of 2x squared, there's not more than one option again. The only way to get to 2x squared is 2x and x, because there are only one set of factors for 2, and that's 2 and 1. As soon as this changes to like a 4 or 6, anything that's not a prime number, then you don't necessarily want to guess and check. It takes a little bit longer to figure out. Okay? Similarly, you can do the same thing on this side. When you think about the factors of negative 1, there's only one way to get there, 1 times 1. We know one of these is going to be positive and one of them is going to be negative, and we can't just randomly choose. It's based on the outside and the inside adding up to a positive 1. So to get to that, I would have to take 2 and 1, and I'd have to subtract them. Specifically, I'd want a positive 2 and a negative 1 to make that work. Okay, so that's your like guess and check method, is thinking through there. But I want to go back to what you learned in Algebra 2, and that was your frowny face factory. You looked at the factors of negative 2 that added to be 1. Okay, and that came up with positive 2 and 1. That's those outside and those inside that we were just talking about. And you were taught about factor by grouping. So 2x squared plus 2x plus 1x, and then minus 1 equals 0. Instead of writing this plus 1, they're replaced with these two things. Then you could group each side. A 2x comes out, leaving you with x plus 1. Over here, the only thing in common is 1. Remember, the sign has to come down. X plus 1 through here. And then from here, oh, I missed my sign on this one. That we decided was a negative 1. And that's why this one switches here. Okay, so then we regroup 2x minus 1 and x plus 1 for our factored point, which is what matches here. Okay, so that is 2 cosine minus 1 and cosine plus 1. It's just a substitution, so we're putting it back in so that I can say cosine is equal to a positive 1/2 or cosine is equal to a negative 1. So the first thing we're going to ask ourselves, are these two things possible? And in the case of this one, they are, because both of those are between negative 1 and 1. But even though one of them's not canceling out here, one of them's one of those nice unit circle values, so we can find that pretty easily. At negative 1, we already decided that gives us pi. Now let's write this one on the same drawing. That's going to be helpful for generalizing solutions if there is a nice pattern between all of them. So cosine is 1/2. That could happen at the right side in a triangle, in first quadrant, or in the third quadrant, or fourth, excuse me. But this side along the bottom is what gets our 1/2, which means here is the square root of 3 over 2, putting a 60-degree angle there. So this one right here is pi over 3. This one would be negative pi over 3 if I wanted to go clockwise, right? It's a faster way with symmetry. Okay, but think about this pattern. It looks like these could potentially be the same distance away. Don't trust your picture, do the math. So here's 60 and here's 60, which would put 120. From 60 to 180 is 120. And then from here to here is 120. So because all of these are the same distance away, I can actually group them together by saying the first answer, which was my pi over 3. And you could start with any of those. You wouldn't have to start at that one. And then I can say they happen every 120 after that. So 120, if you don't remember, is 2/3 pi, but it comes from that divide by 180, tack on a pi. So sometimes you'll have a little triangle happen versus halfway across. You can group any of them. It's nice to do so. Okay. I'm going to have you pause the video and try that last problem, and then we'll check it together. Alright, this one was factors of -2 that had to be -1, positive 1, -2. And we skip straight to sine and sine to get the sine squared. Only one of these was possible, and that's the -1. There are two ways you could write this, going counterclockwise or clockwise if you prefer. I've also written that negative pi over 2. So there is only one possibility, so one answer every period after that. On your homework, you only have one factoring question. We are going to practice a little bit of more of that next class.